Yes. So what is gradient descent? Gradient descent, in fact, it's a first order iterative optimization algorithm for finding local minimum of differentiable function. And gradient descent is very important if we need to use different activation function with a perceptron, or if we need to use error backpropagation with feed-forward neural network, we need to understand what is gradient descent. Gradient descent is an optimization algorithm, and it's iterative optimization algorithm, so we need to run it in iterations. And in each iteration, we will try to make some small changes to our weights and bias using delta omega and delta B. And at the end, we need to stop when we reach local minima, for example, or after reaching number of iterations or epochs. And the idea here is to take repeated steps in the opposite direction of the gradient or the approximate gradient. We can have because sometimes there is a function which does not have any gradient. So we can use the gradient or the approximate gradient of the function at the current point, because this is the direction of the steepest descent. Iterative gradient descent, we call it stochastic gradient descent, and the stochastic gradient descent also we call it online gradient descent. So it's okay. So I don't want to use this one because it. Yes, so we have something called the stochastic gradient descent, and the stochastic gradient descent, they call it online learning. Online learning because we train the model example by example. And if you want to use this gradient descent, we need first to define an objective function or a loss function, which we need to minimize. So very important to define a loss function. This loss function, in case of a perceptron or feed-forward neural network, it could be mean square error, for example. So it could be squared error or mean square error. So we need to define a function, and this function will be function of omega. Do you remember omega? So omega, it's the weights, our weights. And our goal here, in fact, is to try to find the omega star, which will make this Q minimum, right? We need to minimize Q because it's a loss function, it's error function, which we need to minimize. So we need to find a good combination of omega, we call it omega star or optimized omega, which will make this function minimum. So Qi of omega, it's a loss value associated with the i's observation or example. So each example has an associated error called the Qi. So for example, if you want to adjust the weights, so it will be like this one: omega equal omega plus delta omega. In fact, I mean, I don't want you to get confused, but this one, it's the same as perceptual learning rule as we did before. So omega equal omega plus delta omega. But delta omega in this case, it will be minus eta, which is the learning rate, multiplied by the gradient of the cost function. Right? So this one, it's the gradient. And the gradient, in fact, it's the first derivative of Q. So the gradient will be the first derivative of this function with respect to omega, because we try to adjust omega. So as in the definition here, it's first order iterative optimization algorithm for finding a local minimum of a differentiable function. This function must be differentiable. This function must be a differentiable function. And the idea here is to take repeated steps in the opposite direction, and therefore we have negative here because we are moving in the negative direction of the gradient. You are moving in the opposite direction of the gradient because you want to go down. In fact, you want to minimize. If you want to maximize, this one should be positive. Right? So if I will plot this function like this one, I need to move in the opposite direction. This is my function here. This is x, and this is f of x, for example. Right? So if you are located here, I move in the opposite direction of the gradient, so I can go into the direction which will minimize f. So I need to reach that point. And if you are here also, you need to move into that direction. So you need to move in the opposite direction of the gradient. And the gradient here will be negative because the slope here is negative, but the slope here is positive, correct? So you need to move against the gradient in order to minimize your function. So the gradient here is negative, correct? Negative multiplied by negative, it will be positive. So in this case, you will go into the direction which increases the gradient. So in this case, we are sure that we will go in the direction which will minimize my function. If you are here and the gradient is positive because the slope is positive multiplied by negative, so it will be negative. So in this case, we are sure that we will move in the opposite direction of the gradient, in the direction which will minimize f. It's called the stochastic gradient descent because we do it example by example. We need to define the function, right, the loss function, and we need to find the delta omega, and the delta omega will be omega plus delta omega equal minus eta multiplied by the gradient. So that is all. Now we are done with it. So the most important now, it's just to find the gradient. If you have any cost function, you just need to find the first derivative of that function. So we can have something called, there are two types, in fact, of this gradient descent, the stochastic and the batch gradient. The stochastic means I will do it example by example. Do you see here, we have here qi, you know the suffix I? So when you have a new example, you will use this example for adjusting the weights. So we're adjusting the weights example by example for each sample or for each observation, for example. So if you have 100 data points, it means that you will adjust your weights 100 times, one time for each data point. But in case of batch gradient, no, in batch gradient, we try to do it over the batch. So, for example, if you have 100 data points, and those 100 data points, we divided them into two batches. Each batch has 50 observation. So we will calculate the mean gradient over the batch, over the 50 data points. And after that, we will use this mean gradient for adjusting the weights only one time each batch. So stochastic gradient descent, it requires too much calculations, but it does not require memory. Because if you have a computer, for example, and you are training your model, you just need a memory enough for holding or for storing only one observation, one example. Correct? So it will be too much calculations because quick calculations, because in each iteration we need to update the weights for n times. If your sample size of your training data has a size of n, so you need to repeat it n times each iteration. So your computer will be busy with too much calculations, correct? Processor, CPU, for example, it will be busy with calculations, but you don't need to have large memory because we just need only a memory for storing only one example. And once we finish with this example, we will delete it and we will go to the next and so on. So if you are working with radius, for example, you will not have a problem here with the stochastic gradient descent because your memory will be enough for holding or for storing one observation, which will be used for calculating delta omega and adjusting omega. But if you use batch gradient, so in this case we need to calculate, in fact, the average gradient over the batch or the mean gradient over the batch. So I need to calculate the mean gradient. I need to calculate the gradient for each example. And then when I finish that batch, I need to calculate the average gradient. And after that, I will use the average gradient for calculating delta omega. So delta omega, in this case, it will be minus eta divided by n multiplied by this gradient, correct? So it's the average over n samples. And you will use this value for adjusting the weights only one time each batch. So in batch gradient, we adjust the weights only one time each batch. But in case of stochastic gradient, you need to adjust your weights one time each sample. So, so the basic intuition behind the gradient descent, it's just to try to find this hypothetical scenario. For example, if you are on a mountain, for example, and it's foggy around you, so do you see it's not easy to see around. You cannot see too much around you, and you need to go down. In fact, what will be the strategy which you will use? You will try to look into the gradient descent. Steepness. You will look into the steepness of the hill at your current. So you are here, for example, and you will see that and the steepness, it's like this. It's going down here. So you will go into that. You will not go up, but you need to go down. So you look around yourself, and you will try to look for the steepness of the hill at your current locations. Then you will go into the direction with the steepest descent downhill. So you are here, and you want to go down. You will not go up, because if you will go up, chances that you are climbing is much higher, but you need to go down. You need to descend, in fact. So in your location, you will try to look around and try to search for the steepness of the hill, and you will use that direction. You will move into that direction to go downhill. if the opposite direction, if you were trying to find the top of the mountain, which is the maximum point, then you would proceed in the direction of the steepest ascent. So we have steepest descent and the steepest ascent, if you want to go downhill or if you want to go uphill. So using this method, you will eventually try to find the way down the mountain, or maybe you will stuck in some hole, for example, because at some point, maybe you will go down and you will find yourself in a hole, correct? So there is no way again to move forward. I mean, if you will follow the same strategy, it will be very difficult to move because it's the steepest, the steepness is ascent from each direction, not descent. So you can so imagine that you are here in a mountain, for example, you are here in that location, you will try to go into the direction with the steepest descent, and at some point you can stuck in a hole like this one. So maybe you will come like this one and you will stuck here, correct? Using this strategy, I mean, there is no guarantee, right? Maybe because you moved in maybe in direction, you selected this direction and you moved in this direction based on the steepest steepness descent, for example, and you will stuck here in that place, you will stuck here. So we call it local minima. Not. But you want to go down in fact, you need to go down. This one will be global minima, global. But maybe you was not, I mean, you were not so lucky, so you stuck here. So it will be a problem. So maybe you need to start from scratch again and try to find a different direction. So I mean, using this strategy, it has some drawbacks. One of the drawbacks is that you might stuck in some local minima. So you will not be able to reach the bottom of the mountain, but you will stuck in some holes, for example. So you will go down until until it's flat. So you'll go down until it's flat because there is no way to move. So when it's flat, you will just stop because all directions are the same. So you will stop at that locations. So what about the cost function? We need to get, if you need to use this approach, you need to get the gradient of the cost function. First, we need to define a cost function. And this function it should be differentiable, which means I need to find the first derivative of this cost function. So usually we use sum of a squared error, because this function is convex. We need to have a function which is a convex function. So it will be like this one. So we need to find the error. So maybe this one will be omega, right? This one will be error. So I need to define the error as a function of omega. And this function must be convex. To be convex, you need to square the function. If you want to be sure that this function will be convex, you need to square the function. So maybe the function will be like summation of t minus y squared. Correct? Usually they multiply it by half. So it will be like this one. So this one I can call it, this is the error function, which we need to minimize. So the error function or the cost function will be half multiplied by the summation of t minus y squared. Right? This one is squared, which means it will be convex. Why it must be convex? Because we will start from some point and we need to reach the bottom, we need to minimize, we need to find omega, which will minimize. We need to find the value of omega, which will minimize this function, which is that one, omega star. So maybe you will starting from here, correct? By chance, no one knows. Because when we are training our perceptron, we try to initialize the weights with small random values. So maybe you are starting from here, maybe you are starting from here. If you will be starting from here, you need to move into that direction. If you are here, you need to move into that direction. Right? So what is the rule here? We know the rule, delta omega equal minus eta multiplied by the gradient of my function. It will be like this one. Minus eta multiplied by this one. If you are here, for example, and you want to move in that direction. So you can see here that this is omega, and this is the initial value. I call it omega 0, for example. So omega 0 here, in fact, it's less than this omega. So in fact, we need to move in the direction which will increase this omega. Correct? How can we do this? Yeah, so our rule will be omega equal omega plus delta omega. This is delta omega, so it will be minus eta multiplied by the gradient. The slope of the gradient here is negative, correct? In the first part here, the slope here is negative. As you can see here, the slope is negative. So negative multiplied by negative. So in this case, delta omega will be positive. And when delta omega is positive, it means next to omega will be larger than current omega. So in this case, we will move in the direction which will increase the value of omega. But if you are here, what will happen? Here the slope is positive, as you can see here. The slope is positive. Here the slope is negative. The slope here is positive. So in this case, delta omega here will be negative, because minus eta multiplied by the gradient, which is positive, so it will be negative. So in this case, I will force my omega to decrease, because here, in fact, omega star here or omega zero here, it's bigger than omega star. So I need to move into that direction. So I need to move in the direction which will decrease omega. How can we decrease it? By having this delta omega negative. When that part is negative, in this case, the next to omega will be less than this omega, because omega equal omega plus this negative value. So we will subtract a value from the current omega, which means we will move in the direction which will decrease omega. So let us have an example. This is the convex function. Hopefully that our model will be like this one. But in fact, this is, it's hopes, wishes, right? That our function will be beautiful like this one, because this function, it will be easy. If you start from that side or from that side, anyway, you will end up here quickly. But the problem, if your function is non-convex like this one, right? This is very dangerous, because we have here two minima. We call this one, it's global, sorry, this one global minima, which is okay. We need to reach that place, but this one, it's local. It's like going down a hill and you will stuck in a hole in the mountain, right? Because if you are starting from that point, the chances that, you will stuck here anyway. You will go down here and you will stuck here. You will not be able to go out. But if you are starting from that point, you will be lucky, because you will go down to that place, and we will be very happy here, because the error here will be much less. So the prediction error here will be much less, but the prediction error here will be high, and you will stop training. In fact, when you reach that point, when you reach this, we call it saddle point. When you reach that point, your algorithm will stop. Why it will stop? Because the slope here will be negative, will be zero. In fact, the slope of the gradient, and the slope of the gradient will be zero, will be negative, and after that it will increase, and at some point it will be zero. And when the gradient is zero, in fact, delta omega will be zero. So at some point here, delta omega equals zero. So when you keep updating your weights, you will not be able to update it, because delta omega equals zero. So omega equal omega plus delta omega. So in fact, the next omega will equal to the last omega. So you will stuck in that location. Why you will stuck there? Because the slope of the gradient is zero at that point. So if you are starting from that point, you will not be lucky at all, because you will stop here. So the model will stop here. You will train the model for number of epochs, number of iterations. And at some point, you will see that, okay, the graph is not improving. There is no improvement in the learning process. It will be flat, right? Because we stuck at that location. But if you are lucky, and if you are starting from that place or from that place, you will end up here, correct? It will be okay. Otherwise, it will be a problem, because you will stuck in this local minima. So let us take an example. We have a function, for example, it's a squared function like this one. This nice function, it's 5x squared plus 2x minus 4. And I try to plot this function, it will be like this one. So this is x, and this one, f of x. And we need to find the value of x, which will minimize this function. So I need to find that value of x here, which is close to zero, you see? I need to find x, which will minimize the function. This function will be minimum here, because it's here, it's a zero, in fact, right? So maybe -4, sorry, maybe it's a -4, not zero, -4. Because if you put x equals 0 in this equation, it will be -4, right? So this function will be minimum at x equals 0, which is -4. So how can we solve it using gradient descent? As I told you, we need to find the gradient of the function. So this one is wrong, in fact. This one wrong. This one should be like this. So the gradient of x, or the gradient of f, it will be f dash, which means the first derivative of this function. So it will be 2 times 5, it will be 10x, plus 2 times, plus 1 times 2, so it will be 2. So it will be 10x plus 2. This is my gradient. So we will go back to this equation, delta omega equal omega plus delta omega. I will do the same, but now for x. So x equal x plus delta x, right? So, and I will do it with some iterations. We will do it with some iteration. So we will start, maybe if we are starting from that location, for example, we will see what is the value here. So x here equal minus 10. So imagine that we're starting from here. So where x, current x equal minus 10, right? So what is the gradient then now? What is the gradient of x? So it will be df of x minus 10 multiplied by 10. So it will be minus 100 plus 2. So it will be minus 98, right? So this is the gradient. So delta omega equal minus eta multiplied by this gradient. Imagine eta is 0.1. 0.1. So it will be minus, it will be positive. So it will be, I want to select a smaller value, not 0.1. Okay, okay, just 0.1, because we will jump quickly to this point, so no problem. So it will be, this one will be plus 9.8, right? So delta omega equal plus 9.8. So now I need to update x. So x equal x plus delta x. Sorry, this one is delta x. So it will be minus 10 plus 9.8. So it will be minus 0.2. Do you see? So now we go down quickly into minus 0.2 to this point in one jump, because I'm selecting this step size, learning rate equal 0.1. So we're starting from that point. So we will move in the direction which will increase x, right? Because you see the gradient here, the gradient was negative. This is my gradient, negative. So the gradient here is negative. But if you are here, for example, no, the gradient here is positive, correct? So if we are selecting this point as a starting point, which is 10, we will find the gradient at that point. It will be 10 times 10, 100 plus 2. So it will be delta x here, or sorry, gradient of f of x. It will be 102, which is positive. So in this case, delta omega will be minus eta multiplied by this value. So it will be, for example, minus 10.2. So now it's delta omega is negative. Delta omega is negative, but here delta x is positive. In that side, it's negative because I need to move in the direction which decreases x, because here x is 10. So now I will update, right? So in this case, new x equal all the x, which is 10, minus 10.2. So it will be minus 0.2. Oh, wow. So we just go down to the same point in one step. So now you know how it works. You know how it works now, right? So non-stochastic gradient descent, it does not necessarily go towards optimum. The update rule is the same for convex function. I mean, if your function is non-convex, we will follow the same approach, but maybe we will not end up in the local global minima, but we will end up here. This is the problem. So if you are starting from that point, you will end up here. If you are starting from that point, for example, you will end up here. If you are starting from that point, if you are lucky, you will end here, which is the global minima. If you are here, you will end here. So now it is based on, your results will be based on your starting point. When it's non-stochastic, when your function is non-convex, so your results will be based on the starting point. And the starting point, it means in the initial values. So those are starting, because we are talking about omega, right? When you have a perceptron, you have here omega 1, omega 2, we have here bias. So the starting point, in fact, it will be the random values, initial values, which we will use to initialize omega 1, omega 2, and b. Just remember this. So the problem, this is my error function. Imagine this is my error function. And my error function, which I need to minimize, it's non-convex. So some people will end up here, some people will end up here. So you have the same problem, and your colleague, he is working beside you, he has the same problem. Both of you solving it. He reached the local minima, and you stuck in the global. He reached the global minima, right? and you stuck here in the local. So don't worry. I mean, your work is the same, your work is fine, but you are just starting from a point here, but he is starting from here, and it's by chance. It's just trial and error, correct? Maybe if you run your model one more time, if you can try to train your model one more time, maybe one time you will start from here. So how to discover it? How to discover that your error function is complex and it's non-convex? By training your model several times. So you can, for example, say that, okay, I will train my model 10 times. So I will initialize my weights with 10 different random values, 10 different random sets, right? So, and each time you will get the error. We see that the error will be this value or this value, right? So maybe the error here will be 2%. The error here will be 5%. And you will put it in a table, correct? So you can see that sometimes it's 5%, 5%. One time is 2%, 5% again, 5%, 2%. When you look into those numbers here, you can see that you have two minima, one local and one global. This one global, and this one it's local minimum, right? So you will discover it if you can train your model several times, and each time you need to start from different initial sets, different initial values. So in this case, you will be able to discover it. So this is a simple function. I mean, I can explain it using those simple functions, but in reality, it will be something complex like this one. So if you train a machine learning model for solving complex problems, maybe it will be very complex like this one. So you are starting, I mean, it looks like this one. You have lots of local and global minimas, for example. You are starting from this point. It will take time, go down, go down. I need to reach that point because this one, it's a global minima. But also maybe you will stuck here. It could happen that you will stuck here, which is local minima. So in reality, in fact, it's more complex than those simple examples which you are using. This one also, the terrain is very complex. Maybe you are starting from the point here. Maybe you go down here. We need to search for, so maybe it will be very complex. Maybe you will not reach the global minima, but you will stuck in one of those local minimas instead of a global minima, for example. So in reality, it's much more complex than theoretical. Yes. Now we are finishing today, so I will leave this example for next time, but you can go to this example and try to run this example. And so I can just explain it very quickly. So I try to implement the gradient descent with the function which we just described. So my function is 5x squared. This is my function, 5x squared plus 2x minus 4. This is the gradient, which is the first derivative of the function. It will be 10x plus 2. I need to define number of epochs learning rate. I mean, I need to plot it. So I'm selecting values for x from minus 100 to plus 100 using a step equal 0.1, for example. And after that, I will try to simulate my function. And I will start from a point. So this is my gradient descent, that part. This is my gradient descent. So I will start from some point here, correct? And I will update x in each iteration. So x equal x minus. So this equation, in fact, this one is x equal x plus delta x. And the delta x equal minus eta multiplied by the gradient. What is the gradient? Gradient, it's f dash of x, which is the first derivative. So as you can see here, so x equal x minus eta multiplied by the first derivative of the function. And if you are, I'm plotting my function, and if you are starting from some point, where is x? Yeah, because I started, the initial value is this, from starting from minus 90, for example. So I'm starting from here, something from here, correct? X value here. So, and as you can see here, I try to, do you see? So I'm starting from here and I will reach this point, which is, can you see it? So we're starting from here, and in some iterations, we will be able to reach this global minimum. Global minimum. So please go to this example. We will continue from that part, right? We will continue from that part. But until next week, try to go to this example and try to explore it, and try to revise things which we finished. And we will meet again next week at the same time, in the same day and at the same time. And please, if you have any questions, just ask, just give me if you have any questions. And also you can contact me by email or something. Yes, so we will stop here today and we will continue next week. So thank you very much for today.
Thank you very much.
Thank you.
Thank you.